Let's talk about phase transitions and the Ising model.
In our daily life, it is a reality that matter at thermodynamic equilibrium exhibits different macroscopic states. For instance, we can see ice, liquid water, or steam depending on the temperature and the pressure conditions we set. Moreover, water can abruptly change its phase by smoothly varying its external parameters. We say it is experiencing a phase transition. At this point, many thermodynamic functions become non-analytical, and the physics underlying this phenomenon is still not completely understood. With the purpose of studying transition between ferromagnetism and paramagnetism, Ernest Ising proposed a minimal model that would be recognized as the paradigm of a phase transition for theoretical physicists. But why is it so important? First, because it is a simple model that captures really deep physics inside it. Then, because it is the first mathematically solvable model showing a phase transition. And finally, because its very few hypotheses make it easily comparable to other systems, such as alloys or reticular models for gases. Let us now describe it. Ising model considers a configuration of n particles at the vertices of a lattice. Moreover, each particle can only be in one of two different states, up with spin plus 1 or down with spin minus 1, and the energy will only depend on its interaction with the nearest neighbors and an external field. Now we wonder how the magnetization, which is the order parameter of the system, changes with temperature. To see that, we should first construct a Hamiltonian function and make some statistical physics. By using the canonical ensemble, we can deduce that while the one-dimensional Ising model does not exhibit a phase transition, the two-dimensional version does it. In fact, we can plot the order parameter as a function of temperature and induce from there the behavior of the system. Then we'll distinguish an order phase when m is not equal to 0, understood as the state where the interaction between spins force them to align together in the so-called ferromagnetic regime. On the opposite, the disordered state will correspond to m equal to 0, in which thermal energy randomizes the orientation of the particles, leading to the paramagnetic phase, and transition between different states is clearly defined.